Welcome back, everyone. Our final presentation today is by Mr. Sudhakar Surendran, technical lead at Texas Instruments. Sudhakar works in the MCU division at TI. He focuses on analog integration and he has worked extensively on IP SoC verification, emulation, prototyping, and silicon validation. He has 6 publications and 3 patents on verification and microarchitecture. He holds an MSc degree from ISC Bangalore and a B from PSG College of Technology, Coimbatore. Welcome, Sudhakar. I would request you to pass on the mic to anybody who has a question.
Yeah, sure. Good afternoon, everybody. I think you know that our stomach is full. You can get something out here. Before I start off, the one difference you'll see from the previous 2 presentations is from TI we don't have any in-house tool to support Formal. So all the tools that we are using are from the vendors, and the results and my experiences, everything is going to be shared based on how we have used the vendor tools, where we have found effective. And the second difference you'll see, the way we use the Formal is also, we have multiple design groups. It is not like we have one family that we are just supporting and there are multiple generations. So you see the projects being changing every 2 years, the whole life of the project and stuff. So there is other different perspective you'll get from the way we are using the tools. So I tried to make the presentation personal because I didn't know it's not like a paper, right? So I just said this is the way I'm using it, and maybe certain things I can share with you that you can find useful with this. Okay, this is outline, so I'll start off with acknowledgements because it's not my personal work too. It's like the whole group and the various people that I've worked with. I've shared some of their results too here, and I'll share what I mean by formal verification, how I got started, and why I got started. How do I do it usually? I mean, that's one of the questions also we have when you're starting afresh, right? How do I start on it? I mean, it's one of the things that keeps going on your mind. Where I found it effective. I mean, there are a lot of things you experiment also. Okay, I do this, I do that, but this is the right way to do it. So I'll share my areas where I found it to be very effective and faster, and the quality that is coming out. And what are my learnings in using FC? That's, as you see in any part, right, you see that there are certain learnings, certain things where you fall down, and I share those too. And my feel of where I see the formal verification heading and where I feel it will be useful for us, and follow with conclusions. So these are the folks I've worked with and who have mentored me, guided me, and folks who have mentored and guided also. So start with Subir Roy. He was a professor in one of the IITs, and I think he's now again gone to professor. Rajesh Mitra is now with Synopsys, and Arif and Harish, I worked with them to guide some of the stuff, and Arif I closely worked with in collaborative work, and Lokesh from Cadence. And before this, 10 years back, I was working with Mohan from Cadence also to get some of things going on. What do I mean by FP, right? I think we have been talking about FP. Basically, what I mean by FP is nothing but a formal analysis which helps to prove or disprove that the design is actually meeting a formal specification. So if you see, this is a very loaded sentence, and that's why I've actually split some of the terms here. The design here, basically, I mean, it's the design and the test. It is usually the RTL. Here again, the stress is on the word usually because mostly you'll also see some of it being a software like a C, or it can even be a high-level abstractions that you do, not necessarily the RTL. And the formal specification is a precise and unambiguous manner of capturing the properties of the design. So this is, again, what you usually write in your verification plan is slightly different. It's a very colloquial English, but here you need to be very precise in what is going to happen then and how it is going to happen, because once you start using the tool, right, you'll realize that if you're unprecise, you'll see a lot more iterations you're taking. So this is one of the things that you need to be very aware. You need to be precise and unambiguous. If you're again unambiguous, you'll see a lot more errors being thrown out in the way you do things. The presentation I'm going to focus on is based on assertion-based verification. That's why I've written there. It is usually assertion-based verification, but formal is not constrained to assertion-based verification. There are various other ways of doing it too, but the way at least we have used based on the industry available vendor tools is assertion-based verification. And again, as the last item, I think we have seen a couple of presentations, one from Kiran on how their internals of their algorithms, and again from Sudhakar from IBM on how the internals work. But I'm not going to touch on the internals. My rest of the presentation is going to be on how to use it. So why I started on FE? Okay, if you see the presentations and the training, you go right, they said, okay, it gives you a complete design coverage for any given property, and they say that no additional TB needs to be developed, and it is faster verification. And they also say that RTL designers can code, so the DV guys cannot do it. If you see these 4 lines, it is a direct sell-off for any verification guy. It's easy walkthrough for me. Okay, all I need to do is push the tool, and I'll be able to get what I done. But again, I'll revisit these 4 items, at least the way I was bought into and what are the pitfalls in that. But this is how I got bought into the tool and how I started working on it. How I started is training. Basically, had a training from parents on how to use their IFE tool, and I started using some toy examples to play around with. Okay, what to do, how to do, and still I was not comfortable with it, because once you start doing the toy examples, you'll realize that there are certain expertise levels you need to get. So what I did is what I know already is simulation. So I started off with simulation-based, assertion-based verification. So I started coding simulation-based assertion verification and slowly started to apply the same thing on the formal. So that is how I fully went into formal. So these are stages I went through. How finally I went through full IP level DV also. So how I do it, first and foremost, I'd like to very clearly mention is the planning for formal verification is much stringent and disciplined than what you usually do for a simulation verification. The word stress on the word here is integrated. Actually, it's an integrated formal simulation and design. Actually, why I'm saying formal simulation design, you'll see as we go through the slides, because formal is not going to be a complete solution for you. So you need to have some things you need to do in simulation too, and there are certain lot of help you'll need from the designers to make sure you are able to achieve your goals. First thing you need to do is you analyze, partition, and parameterize the design. You cannot do it. What you need to do is when the design is coming up, you need to have a close interaction with the designer. One advantage at least we have in TI is it's like a flat hierarchy. So I just sit with my co on the RTL side. I just talk to him, I influence him, just taking for a coffee or lunch, and then say, okay, what are you doing? What are your architecture? Sorry. So I just work with him and then have some blackboard sessions and then try to understand how the whole microarchitecture is structured, and then see how I can partition the design so that I can write assertions that are manageable. You can still write a very complex assertion that goes into 5 or 6 lines that will meet from your input to the output of the design, but you'll make a lot of mistakes in it and you'll spend a lot of time trying to make sure those assertions are coming out correct. So you need to actually pipeline your assertions so that you manage and solve simpler problems, but at the end of the way, if you look at from a top level, you see that the whole problem is getting solved. So to do that, you need some amount of design partitioning and some amount of design parameterization. For that, you need to work with the designer. So to do that, you need to start engaging with the designer from day one and then start having discussions with him. So it needs to be a back and forth. It is not like a one-way street. You need to have a two-way street where he also gives you ideas, you give him ideas, and then make sure at the end of the day, the goal should be to get a bug-free design and a very faster. That is the time to market is the goal, and quality is the importance here. So what you can identify here also is, as I stressed here, is one of the things is where formal easily applies is, or I wouldn't say easy, where it finds its value is on the weak sections of the design, because once you start talking to the designer, he'll say that, boss, I'm not very comfortable with this portion of the design because I'm finding a lot more bugs, or my coding and the way I've reviewed it, I still see something going on wrong here. You may need to strengthen your verification here. So those kind of words, if you can pick out, you'll know that these are the sections of the design I need to apply the formal. And critical again here is there will be a very important stone in the whole thing, that if you pull it out, your whole design is going to fall. If that feature is not there, then there's no point in selling the chip. So you need to pick up those kind of features and then say, okay, these are the areas I need to definitely prove my quality. And there again, you will see a lot more buy-in from the management also coming in if you're spending a lot more effort. As the earlier speaker said, it is not an easy walkthrough. You need to spend time on it. So it is easy to get buy-in to spend a lot more time once you are focusing on the weak and the critical designs. And control sections. Control sections are better for SE mainly because this is again coming from the vendor-based tools, because we are not focused more on data, but and other thing we also realize is since we synthesize our data parts, we don't use hard-coded data parts like the other speakers who have talked about. We don't have that issue of making sure our data parts are indeed what they're supposed to do. Our main focus now is going to be on the control part. That is where we are going to find a lot more issues. And we found that it is difficult to verify all the corner cases and coverage points in a control. If you are able to structure it in a proper set of assertions, you'll be able to get your control path much more quality out. I think the partition thing I want to, as I was saying, right, if you partition your design, then you can make your assertions to use assume guarantee approach they usually talk about. So once you apply it on one block and you interface with the next block, whatever you use as assume in the previous design now becomes your assertion. And you'll have a common set of things that based on how you look at it, whether at the IP, at one IP to another IP, you see certain assumes becoming as a property. So this is actually a very useful method. I felt that which enables you to split complex properties and also to manage your whole runtimes and stuff like that. Parameterizing is another thing that you need to be very watchful about, because as I said, even though you are focusing completely on control, you still have certain things of data path coming like FIFOs or some data going from one side to another, like you have huge buses going from one side to another. How parameterization helps is the way formal works is even if you are having 1 or 2 bits, you will still be able to prove if there are no transformation on the data happening, you will still be able to prove your data path and the control path is still working. So why I need to do parameterization? Because the tool sometimes will give up saying we are having huge number of things. That's I think in the IBM presentation we saw, right? I think it gives up, but to handle it, you can parameterize the design and say, okay, if the tool gives up, instead of having 32 bits, I'll try with 16 or 8 or 2 bits, and you'll see that your property is still being proven on the complete design. And another important thing is it is not just design, right? Assertions also you need to plan properly. You need to work with the spec owner to write machine readable spec. This is again a very critical point, because you will again see that if I am doing a combo logic or a control path, there are certain areas where you see this being repeatable or the functionality is similar. If you are able to get a spec writer to give you in some standard machine readable form, then you can actually process that machine readable form, use a assertion template and dump out auto assertions and then apply on your design. So I'll show some examples where we have found this useful. And this again you need to work with the spec guys to make sure they're writing in a form that is machine readable. And check if already verification IPs are available for assertions. Like for example, from Cadence you have those AMBA VIPs already available. I think there are some more they support. So if they are already available, you don't have to do any work. All you need to do is interface your DUT with those assertion VIP and you are good to go from day one. I mean, it is not day one, it takes a couple of days to figure out the right configuration, but at least you don't have to spend a couple of weeks to write your complete set of assertions. Other thing is there are apps. There is a new thing that is coming up, what they call as verification apps from the vendors. I think each and every vendor has their own set of verification apps. Cadence has its own set. I think Jasper now, whatever is integrated, they have their own set. I think other vendors too have their apps. Look for opportunities to use those apps. You will see that again it will help you to get faster to the end goal. And last, one of the important points is to, as I think I keep stressing on this because usually when I talk to the RTF verification folks, they say that, boss, you cannot do this because it takes from end to end and you need to write a very complex property for it. I keep stressing that if you are able to partition and then pipeline your assertion, you will actually be writing a very simple assertion, which is not only one line assertions, but it will be 5 or 6 assertions, and you will still be able to meet the whole goal of the end-to-end assertion. So there are a couple of things I said, okay, you can break it at design boundaries or break it into multiple mutually exclusive properties, or you can do split again. So if you're trying to write a property which is complex, for example, I think one of the gentlemen asked, how do I do a protocol verification, right? So if you're trying to write a complete property for a protocol, it becomes very difficult. What you can do is you can do a very simple model that you can build for checking the which actually implements the protocol, and you can write an assertion on top of the model. So it is like a model checking between your TB model and your RTL. The difference is the RTL has much more complexities involved. Like it may have to handle before, it may have to handle multiple clock domains, it may have to handle power domains. Your TB model is very, very simple, which is nothing but a protocol conversion. That's all it is going to do, and you can use that to directly apply. Write a very simple property on the TB model you have built in and the RTL, and then make sure it is indeed matching. Other important thing is, this is one of the main important pitfalls also of formal verification, is we tend to write a lot more constraints and assumptions, and if you don't have a very good way of verifying those constraints and assertions are indeed correct. Constraints and assumptions, not assertions. Constraints and assumptions are indeed correct. You will actually see that the completeness that you are getting is all lost, because you would have made a wrong assumption and you will actually make sure you have got a bug into your design. So you need to have a lot more reviews, and in the previous example, the way I was showing you the assume and guarantee, right? You can even plug your assumptions from one block to another. Other way to do it also is plug those assumptions into your simulation environment and make sure you are able to verify your assumptions are indeed what they are supposed to do. Again, parameterization, again, this helps you in the data part that I explained before. Last but not the least in the planning is execution. So you need to plan what all TB models you need to build. You need to look at your tools itself, right? Since we are using just one vendor, but we also reviewed multiple other vendors and seen what is the best thing. You need to know what options to use. But again, this is all, when you're going to advanced stages, you can look at all the options, which engine to use, which is more optimal. But to start with it, at least you need to know basics of how to use the tool. That you'll be able to get in the training. And you need to have a fallback plan to go to your simulation. Mainly for one of the things I was saying is, right, to check that your is not assertion, it is actually, it's also the assertion correctness, because usually when you're moving from simulation to formal, right, one bigger wall that you will face is, in simulation I have the feel of, I can look at the waveforms, I know how it is progressing, you will see things going around smoothly. But when you go to formal, it says yes or no, but you don't have the feel of what exactly is happening, am I doing the right thing? You still have those doubts in your mind. To clear up those doubts, you still need to do some of these assertions ported into your simulation environment, and you will be able to get comfort level within yourself that whatever I'm indeed doing is correct. So, but again, once you go to the expert level, you don't have to do that, but at least to start off with, you can do that, so you get more confidence in what you're writing and what you're doing, because at the end of the day, you guys are going to qualify and then say, put your stamp on it, yes, I'm certifying it. You need to be confident about what you're doing. There it helps a lot. And I think in the IBM presentation, you saw that hybrid flow, right? There, that's what we call as a state-based exposure. So you need to sometimes guide your formal tool to certain important states. For that, you need to have some simulation environment to guide it there, and then it explodes there. So to do that also, you'll need to fall back to simulation. And you may need to do some amount of coverage improvements. I think coverage is again a very touchy topic when you go to FE, because each one has their own ways of doing it, but still you don't get a complete feel of what is happening in the coverage, because each vendor has says, okay, you have covered these. But to still get some feel, you still need to go back to your simulation environment to say, okay, these are the coverages I have indeed covered and stuff. And the fourth point I would like to say is have a plan B, because at least if you don't have a dedicated formal verification team and you are doing both your simulation and the FE in it, right, you need to plan for a plan B in cases where the tool gives up, because you will have an end date and somehow you need to meet the end date. And you will need to have a read points in saying, okay, beyond this point, if I go, I'm not going to be successful if I continue on the formal side. You need to have a plan B and then move to your plan B. The plan B can be as simple as working with the vendor who is supporting you to say, boss, this is not working, get me to work. Or it may need to have something more saying, okay, I'll prove certain things in formal, move certain things out based on the complexity. This again goes back to the initial planning I was saying, right? Design, analysis, partition. There again, you will see that you need to plan it so that you will have a plan B for certain cases where you see it is not working out. And the last point is the coverage, tracking, and the closure. Here you need to understand what a tool is saying as covered or not covered, because each tool has its way of saying a coverage being reported, how they are being reported, so that you know if it is indeed saying covered, is it really covered? that question you need to answer. And having additional the cover properties, I think the other two speakers spoke about. Where I found it effective is, I think first thing is very straightforward, right? I think if it is simple, not simple, if it is a complete combo logic, the tool can easily handle it, and all you need to do is have a very good set of assertions. Examples I have given is the pin multiplexing logic. Usually in the SoC, you will have multiple I/O pads, and you will have a huge amount of multiplex happening between your various IPs. So this is a very useful way because you will see a lot more automation you can do. This is where again I was talking about the working with your spec owners to give it in a very mission readable form, so that you can. It's a very simple assertion template you can use, and then dump out the assertion you can just apply there. And module connectivity, again, one of the gentlemen pointed out, right? You can do module connectivity at the SoC level based again on a template. You can use IP exact to import your pin names and then do a lot more automation on top of it. Mux control logic for interrupt DMA. So these are again simpler examples, but you can still extend beyond, like I think clock gating was one of the things that was pointed out, right? That again is a very good way of, it is simpler in terms of the tool to handle, but you can still make very silly mistakes and it is easy to catch it here. The next level is on the bus matrix and protocol conversion, because bus matrix is again something at the SoC level you see a lot more things being connected. You do have some amount of simulation verification, but I think some of the, if you are buying the bus matrix from a vendor, they already verify it and give it to you. But if you are building it your own, the advantage of the bus matrix is the protocols are all very same. It is not going to be changing from one side to another. It's the same protocol, and once you develop one VIP which is parameterizable, you can apply it across all the masters and slave and then make sure they are hooked up properly, and you will actually be able to catch very interesting issues also there. And again, the protocol converters bridges what we call converting, because if you are having from APB to AHB, all those kind of protocol conversions, here again, it's a more of a control specific thing, and usually RTL designers miss very simple things there. I mean, it's simple when you find the bug, but to think about it, it's small corner cases which you'll be able to catch here, and it is very useful that you have found. And other easier way to get into this is, you, like as I said, right, if you're using AMBA, some of these industry standard bus protocols, the VIPs are already available. You don't have to do any work. You just have to plug in those VIPs and you'll be able to get started from day one. Yeah, system critical checks. This is another area where I have found very useful, because hang cases in the system are completely no-no. And this is a very, very useful place where I found it. You will also see that it is not difficult to write some of these properties. All you need to say is the ready is not hung under certain condition, and you can let the tool run how much ever time it wants, because the very few properties you are trying to check. So this is and this is again a very critical area also for your whole SoC. If the system is getting hung, then it is a problem. If you make an access, or this the way the bus matrix makes an access, if I'm just switching between multiple IPs and stuff, you need to make sure that your ready is not hung. And there may be certain other cases also like this, like if you're having a cache controller or some kind of a protocol conversion between a memory and your CPU, if you're having a huge amount of prefetch buffers and things like that, there again you may want to apply these cases of hang and critical state machines. I found it very useful, and this again, as I said, right, if you are able to convince yourself this is a critical module, you'll be able to get buy-in from your management to say that you can spend the extra amount of time that you need. And because this is like a make or break feature. Critical state machines, again, so as this again, I think briefly touched upon when I said that clock gating, right? Critical state machines, like power state machine, right? They are again repeatable, they are small state machine, but when you integrate everything together, you'll see that the interactions become very complex, and it's very difficult to verify all the use scenarios, how you bring up each and every submodule in a whole SoC. So there again, it's very useful. Yeah, this high-risk state machines, what I mean is that the cache and things like that. And I think RTL optimization, I think the IBM team and the internal team touched upon as a sequential equivalence checking. Here again, it is not straightforward SLEC, but you will still see a lot more optimization being done. So if you look at it from an industry standard tools, you still have SLEC tools, but some of the tools won't be able to handle some of the optimizations you're doing. So you may have to fall back to your formal verification tool to get some of these things verified. And the other thing also trend that I've seen in the last 10 years is the way folks use it in a non-conventional way, non-conventional verification way. That is, one thing is for what at least the latest thing from the Cadence tool is you can build the coverage exclusion files both for your simulation. So because you'll see a lot more dead code or toggle coverage based on the tie-offs or static bits and things like that. So you can import your coverage exclusion file by running something on the FV. Other thing is the uninitialized flops. When you go to VLS, you can figure out what are uninitialized flops and then get it there. And other thing also I've seen is pattern generation for ATPG place. So if you're having 100% test coverage, you need to write some functional patterns to get that coverage. So you can actually tell the tool that these are the flops I want to toggle, and you can write an assertion for that and let the tool figure out the sequence that you need to apply to get the flops to toggle, and you'll be able to get that out. Other thing, it's similar to the ATPG where failed pattern generation is once you have a silicon bug, right? Sometimes it's very difficult to figure out what, because you see that your verification test cases are complete and stuff, but why is this bug coming? You need to go through a lot more iteration events, then you won't be able to figure out sometimes. So this thing where you can just capture in a property in the way the sequence comes, and you'll be able to give it to the tool, and the tool will prove it to you what sequence you need to apply from your bus interface to get this thing done. My learnings, planning. If you don't plan properly, I think you're about to bound to fail, and this is very much applicable for FE because it is more skill intensive, and you need to work with multiple stakeholders. You need to work with your designers, you need to work with the spec owners, and sometimes with the management too. So if you plan it properly and then export your whole plan, then you'll get a buy-in to do what you want, and you'll also not face a lot more hurdles when it will make your job easier. That's all I'm trying to point out there. Again, the next point again relates to planning. It is not a complete DV activity. You will need support from the RTOs and the spec owners. This is one of the fuzzy areas that if you are going completely into FE, right, the question comes, how do I check the correctness of the assertions? Yes, assumptions and assertions, how do I check the correctness? You need to come up with some novel ways. I think Synopsys has recently acquired the certitude. It does some level, but the problem with that is how many runs you do and things like that. So there are certain things you can do, but you need to be aware of this at least, that assertions correctness is very important, assumption correctness is very important, because garbage in, garbage out is very much true in this FE scenario, because if you get even a very small mistake of making because as you don't get the feel for waveforms and stuff, you won't be able to catch it also so easily. So that is why you need to move back and forth between simulation and FE. Yeah, one of the things I've usually seen is using output ports and assumptions without having a relevant constraint or assertion for them. Yeah, I covered this. Yeah, I'm just revisiting why I started on FE, right? Okay, they say that complete design coverage is there. Coverage is as good as the quality of the assertions and the properties that you write. If you're not able to think of all the properties of the design, then you are going to have a coverage hole. You need to have something to plug it. No additional TB need to develop. This again is not true, completely true, because you need to develop at least some simpler TB models to get your assertion simplified, and sometimes you need to develop models to abstract your environment, like the protocol example I was giving. But the models that you develop are not that complex as you do for the normal simulations thing. So that's where you still see, even though you're developing models, it is not a complete whole flow that you're doing. Again, other notion that we say is, okay, I get a faster verification closure. This again is false, because the complex designs, once you start applying FE into, you will see that you will need to spend a lot more time than what you do in the simulation-based verification. But the quality is definitely better that you get, and you need to, that's why I keep stressing the point, you need to know where to apply FE. As I said, some of the sweet spots you will see, and sweet spots in the sense it is not simpler to do, but they are critical to do too. So you need to apply there, and you'll see the cost benefit coming out very clearly there. And yeah, the last point is The RTL designer also can code it, but usually you don't see that the RTL designer is actually coding it, with exception of very few companies like ARM and some of the other folks. They force it the RTL designers to do, but usually they don't do it, and you need to work with them to figure out how to do it. So this is what I see as where the FE is heading. I definitely see FE being made as part of IP and SoC verification, because I'm already seeing it in the way we are using it and stuff, from the way it was 10 to 15 years back and how it is now. At least even a fresher comes and asks, I want to do FE, how do I do it, and I want to do these things. So definitely it's becoming one of the important tools in the verification engineers toolbox. Verification apps and VAPs. This again is a very growing area where I see, and where we also need to be aware, and we can again influence the vendors and the third parties to see what are my apps. I think she touched upon it as a PAX that she was calling it. I call it as a verification app. So this again is a very important thing that needs to be look out for, so that you can easily get started on day one. That's actually the main advantage of it, and you don't need to worry about the correctness of the assertions and things like that. The third point is on tools to check the assertion correctness or the code correct by construction code. So this goes back to the point I was stressing, right? If your assertion is coded wrongly, then you miss out. So you will see some more coming on this sector, that how do I check the correctness of the assertions, or tools that actually say, okay, I can describe what I want from the property at abstract level, and the tool will dump out the assertions I want to check. Yeah, I think the incremental design is that SLEC thing I was talking about, but as SLEC is a term that you can use, but the tools per se, if you see it, is not just a SLEC. You'll need much more improvement once you see a lot more variations coming in your design. Again, there are a lot more, once the skill level of the engineer improves on the FE side, right, you'll start using some of these in research projects. Like one of the things that at least I'm seeing is more non-verification use cases. So you'll figure out that since it's a mathematical problem you're trying to solve, if you look at it that way, you can throw any problem at it and solve and give it to you. If you start thinking in that direction, you'll see a lot more ways of using it, and it will also, again, at the end of the day, it's trying to help you to get time to the market faster. Analog equivalence check, this again is one of the growing things that I see, that if you're having a model and a schematic, how do I check that it is equivalent? Hardware software co-verification. I have built a firmware and I have a hardware for it. Integrated together, are they meeting my goal? So this again is another area where I see things going on. To conclude, I shared what, why, how, and where my learnings and my views on where I think FE is going. To summarize, right, so I see FE is a very unique tool that can be used by any DV engineer to extract what he wants out of it. It's up to left to your imagination how to use it and get things out of it. But you need to be a bit more disciplined to use it and a bit more planned. That's it. Thank you.